Here in this lecture, I'd like to finish up a couple of the quick details associated with our momentum unit that we're talking about. Here in this video, we're going to talk about how to calculate the center of mass of some system and why we care about such a position. And finally, at the end of the lecture, talk a little bit about the rocket problem. So to start and motivate what we would like to do, it turns out that while we've had this discussion of kinematics, where we were looking at position, velocity, and acceleration as a function of time, we didn't pay too much attention to the size of some object, or what point on that object we cared about. And we looked at some small objects like balls, and we looked at large objects like cars. And what point on that object were we keeping track of? What were we calling the position? What were we calling the velocity? How that particular position was changing as a function of time. We don't even know what the position was. What point did we care about? And maybe there was some arbitrary nature associated with kinematics. We could just pick some position and map it. Okay, fine. But now we move into Newton's laws and we started to look at forces. And sure, we could apply forces in certain places. But some forces we didn't have control on where that was applied. One of those forces is the weight. We don't get to pick where the weight is applied, but it has to be applied at some position. And so I'd like to figure out, okay, what position was that? It turns out it's going to be the center of mass. Okay, and we'll talk a little bit more about that. And the same is going to be true when it talks about energy. What position were we really mapping? As we get into collisions, what position were we mapping? In each of these cases, it was the position of the center of mass. And it turns out where those forces are being applied is somewhat important. And we're certainly going to see this in our next unit that we discuss on rotation. Because we can distinguish between some object that is rotating and some object that's not rotating. And we might not know a lot of those details yet. But applying forces in some unexpected ways could lead to rotation. So let's say, for example, I was trying to hold on to a sledgehammer. And I was, so it's a hammer, and I'm trying to hold it sideways. So the hammer head is sitting over here, and I'm holding onto this handle. This is very difficult for me to hold. The head of the hammer is going to want to fall, and it's difficult for me to hold that thing up. Whereas if I was to move my hand over to very near where the handle is, it balances. So by me applying a force in some specific place, I can completely counteract another force. So we don't get two forces being applied at different positions. If we apply those forces at the same position, all of a sudden we don't get this rotation. And we're going to see a lot more of that next time. But that position where the weight is being applied to some object is a special position called the center of mass. And that being said, well, if that's a special position, if we were wanting to map this position in a Newton 2 problem, if we were wanting to map this position in a kinematics problem, if we were wanting to map this position in some expression of momentum, maybe how to calculate the position of a center of mass could be interesting, maybe it could be important. So let's quickly go to OneNote here and look at what it means to have some center of mass. And there's some words here, but essentially the way we colloquially think of the center of mass is a position where some elongated, extended object happens to balance. Sometimes this extended object is made of discrete masses that are separated in a particular way. And sometimes it's something continuous, I don't know, like an umbrella or like a sledgehammer or whatever these things happen to be. But we all have a vision in our mind what it means to balance. But in a calculation sense, what we're calculating with the center of mass is basically the weighted average weighted is kind of loaded, right? But it's basically a weighted average of where the mass is sitting. In some parts of our object, it could reside where a lot of the fractional mass of the object is sitting there, and other parts of the object less so. The head of a sledgehammer has a lot of mass in it, but the handle, even though it's much, much larger, has less mass in it. So how do we go about calculating a center of mass? by using the weighted average of where the mass is sitting. Well, what it means to have some weighted average is we look at some fraction of the mass. This is like m1 over m1 plus m2. Maybe we have just two masses. And we want to look at what percentage of the mass is sitting at a particular position, what percentage of the mass is sitting at some other position. That's what weighted average means. But there's nothing that says that algebraically we can't take this same expression and just group the things together. Here we have the same denominator. Why couldn't we just take m1 x1, m2 x2, and work with those terms instead? In either of these scenarios, if we were to take, let's look at a particular scenario shown right here, where at position x1 of 1 centimeter, we put a 1 kilogram mass. And at position 2, sitting right here, at 5 centimeters, we put a 5 kilogram mass. I'd like to calculate where the center of mass is. And just like in the case of a sledgehammer, it's going to balance pretty close to where the head of the sledgehammer is, right? So I would expect some center of mass position somewhere over here associated with maybe a handle shown in this kind of scenario. Although this is not a sledgehammer, okay, this is not a continuous system. But let's do a little bit of the math here. x1 times m1, 1 kilogram times 1 centimeter. This is just 1 kilogram centimeter. x2 times m2, 5 times 5 is 25 kilogram centimeters. So on top we've got 26 kilogram centimeters divided by 6 centimeters, or 6 kilograms. So we've got 26 divided by 6, 4.3 continuing, so 4.3 centimeters is where the center of mass is, which is pretty close to where the large mass is. So this works essentially the way that we want. And we don't have to limit ourselves to just 2 particles. We could have as many particles as we want. You want 100 particles? Great. You want 1,000 particles? Great. No problem. But the way we're setting up these calculations are we're figuring out some percentage of the mass at position 1, percentage of the mass at position 2, percentage of the mass at position 3, so on and so forth. And it can be written with this form. Or more elegantly, by using summation notation, where this summation in the numerator is mass 1 times position 1 plus mass 2 at position 2 plus mass 3 at position 3 plus mass 4 at position 4, so on and so forth. Whereas on the bottom, we're just looking at mass 1 plus mass 2 plus mass 3 plus mass 4. On the bottom, we have the total mass. We can call that big M. On the top is where we're doing this weighting. Where are the masses sitting? And if we were to take kilograms times centimeters divided by kilograms, this really is going to give us a position. Now this is how we would go about calculating the center of mass in a one-dimensional system. Say it's moving in the x direction. But there's nothing special about what's going on here. We don't have to have mass just distributed in the x direction. We could have mass distributed in the y. We could have mass distributed in the z. There's nothing weird or different about that. So if we wanted to calculate a y or a z component of center of mass position, we could do the same sorts of calculations that we do here. All we're doing is weighting with y or z instead of with x. And if we put all of these 3 forms together, we can find a 3-dimensional vector that points from the origin to the center of mass of a 3-dimensional object by using a summation that looks like this. Where are all of the individual masses sitting? And maybe some of them are to the right, maybe some of them are to the left, maybe some of them are towards you, maybe some of them are up. But I just need to figure out what mass is here, what mass is here, what mass is here, what mass is here. That's what I need to figure out. That's what this summation is doing, and that will give me the center of mass of that distribution of points. Well, what if we wanted to do something that was continuous, like the sledgehammer, like an umbrella? That's not discrete masses. That's a continuous set of masses, and where there's a large mass density at the head of the sledgehammer and a smaller mass density in the handle, how would I work with this sort of scenario that's not discrete masses? Well, essentially what we're trying to do is set up an infinite sum of differential masses. So those differential masses are sitting at real positions in space. So this R and this R work exactly the same. But now I'd like to make these little masses differential masses instead, and then do a summation, an infinite sum, over those different differential masses. So we're basically going from a summation of discrete masses here to an integration of continuous masses here. Now, one thing that I noticed, to find the position of the center of mass, I'm integrating over all kinds of differential masses. And that can be kind of weird if we were looking at a system like a sledgehammer. So the head of the sledgehammer here it's made of steel. It's got a very high density, and we're doing little differential chunks of mass. But a differential chunk of mass in the head of the sledgehammer is a different size than the differential chunk of mass sitting here in the handle. And so now I have to keep track through bookkeeping of how big each of these differential masses are so that I can integrate all of them. And that's a pain. We don't want to do that. What is more convenient for us is to instead figure out what the mass density is, the mass per length, for example, and then we'll just integrate over a length that I know. That's something easy to set up an integral for, but I need to know something about this concept of density. So that being said, if we wanted to create some differential mass, but instead set it up with integrations over a length, integrations over an area, integrations over a volume, we need to come up with these densities. So here I have lambda is a mass per length, sigma is a mass per area, rho is a mass per volume. Looking at units, mass per length times a differential length is a mass. Mass per area times a differential area, that's a mass. Mass per volume times a differential volume, that's a mass. Each of these things has the form of differential mass. But what's nice about this expression is I can put the functional form of where the mass is sitting in my problem inside this term like the lambda, inside this term like the sigma, inside this term like the rho. So in the case of that sledgehammer, the handle has a very low mass per length through the handle, very, very low, but then over here, through this chunk, we've got a very large mass per length. There is a functional form of mass per length that changes over the length of the hammer. But writing it this way, I can put that functional dependence inside this variable right here, and then I just tell the integral, integrate over the hammer. Don't sum up all of these differential chunks, just make sure that you integrate the whole hammer. That's all we're essentially saying with this. So if we were to go to a piece of paper instead, if we were wanting to calculate the x position of a center of mass, and we have this 1 over big M, normally this would be like an x dm, right? Now we're going to write our dm, and just for a one-dimensional problem here, as some mass per length times differential length. X lambda d length. And now if we wanted to go over some system, we just have to say what length are we integrating over. So let's look at a particular scenario here. Maybe I've got some system here. This is x equals 0. This is x equal L. But I'm going to make it out as maybe uniform cardboard or something like that. But the functional form of this is some constant times x squared. So this is parabolic. You tell me where you are in x position, and the mass density is going up as a function of that x, parabolically. And so it would look like this. If this was a uniform piece of cardboard or something, obviously this differential chunk dl has a lot more mass than this differential chunk dl. The width of these things is the same, but they don't have the same amount of cardboard. They don't have the same amount of mass. But using this formalism, now all of a sudden we could do 1 over m. We just take x. What is my density? Alpha x squared. Integrate over dx, and I'm integrating from 0 to L. This is integrating over this whole thing. So this is alpha x cubed dx integrated from 0 to L, which is 1 over m. Now this is 1/4 alpha x to the 4th from 0 to L. And so this is 1 over the total mass, 1 over 4 alpha L to the 4th. I still need to find what the total mass of this piece of cardboard is. And so if I wanted to find that, what I'm integrating is the density over this length. This is mass per length. Integrate over some length, that's going to tell me what the total mass is. Here in this case, we're integrating from 0 to L. So taking the same lambda that we just had, the integral of alpha x squared dx from 0 to L is 1/3 alpha x cubed, putting in the limit 0 to L, which is 1/3 alpha L cubed. I can take this total mass, throw it in over here, and we find that the position of the center of mass is alpha L to the 4th over 4 divided by alpha L to the cubed over 3. Alpha cancels with alpha. L to the 4th divided by L over 3 is just L. The position has units of position, and as you might expect, the position of the center of mass is to the right of the center. And sure, there might be different amounts of mass on each of these different sizes, but the position of the center of mass, where it all balances, and how it is all sitting in respect and relationship to the position of the center of mass, that's kind of interesting. So this leads us to a function of why do we care? Why are we even spending time talking about this position of the center of mass? And for that, let's go back to OneNote. Let's say we wanted to find the velocity of the center of mass. What we might do is take the center of mass position and see how that center of mass position changes as a function of time, as is shown here. All we're doing is taking a time derivative of this thing that we already calculated on the previous page. But because masses aren't changing and the mass distribution is not changing, really the only thing that changes as a function of time is where all of those masses are sitting, right? The mass, those discrete masses, or continuous if you wish, are all the same size. They're just moving, that's all. They could be rotating, they could be doing all kinds of crazy stuff. But the summation and the way that we look at this is all still exactly the same. But this calculation of the change in each of the positions of those individual masses as a function of time is just a calculation of the velocity of each of these different masses, m sub I. So if I have an m sub I and I essentially have v sub I, this is just the momentum of each of those particles. And some of those particles could be moving to the right, some of those particles could be moving to the left. All these particles could be moving in weird directions, but if I sum all of them together, that's the total momentum of my system. So by doing a little algebra, what I see is that the total momentum of my system is the total mass times the velocity of the center of mass. So if I know where the center of mass is and I know how much mass I have, that is the momentum of my system. And each of those individual masses could be going in all kinds of crazy directions. But the point is, if I know where the center of mass is and how the position of the center of mass is changing as a function of time, I know what the momentum of my system is. That's what it is. And, so when it's one mass or two masses or something, you could start to do some tracking of what these things are. But let's say we were looking at a firework explosion or something like that. Now this thing that was initially very easy to track is now much more difficult to track. It could turn into thousands of particles after it explodes. But the position of the center of mass is doing that thing that it was doing before. Now this is just a relationship with momentum. This momentum stuff is a little bit weird. How can we relate this to things that we might have done in the past? And for that, we might want to look at the acceleration of the center of mass. Now that is going to be the change in the velocity of the center of mass with respect to time. Or using this expression that we found above here, we do a little bit of calculation and we find out that the total net force on some set of masses is that mass times the acceleration of the center of mass. So all of those Newton 2 problems that we did a couple of weeks ago, that point that we were looking at, where do we calculate what the center of, or what the net force is going to be? We're applying those net forces at the center of mass. And that's where all that mass is. So once again, in the case of some firework, it's a little bit more complicated to follow. It's following some parabolic arc. It then blows up, and all of those individual masses go in this whole array of different directions. But the center of mass of all of those things that blew up is still following the parabolic path that it was before. So I might have difficulty keeping track of individual particles after the firework has exploded. But I can totally keep track of the center of mass. Totally. Or let's say we were to take the case of some weirdly shaped object, like a sledgehammer, like a tennis racket or something, and I wanted to throw it. And maybe it's doing all kinds of weird motion. The handle is really large and easy to see, the head is really small and doesn't track the eye as well. And you look at the motion of some weird object like that, and it does all kinds of weird stuff. But if you were keeping track of the center of mass of this weird-shaped object, it would be following a perfect parabolic path, just like all the stuff that we were doing from kinematics a couple of weeks ago. So that point that we cared about in kinematics was the position of the center of mass. That point that we were keeping track of through all of the various accelerations brought about because of net applied forces, that was being applied to the center of mass. These collisions and multiple kinds of particles, and how we keep track of their position and how the position of those particles changes as a function of time is really built around this idea of the center of mass. And so knowing about the center of mass is really, really important for us to know, because that's really the point that we were keeping track of. There are a couple of videos that you could watch associated with this. These are the MIT videos. They show up kind of weird in the Canvas page, but if you actually go to YouTube, it will let you watch those. And they're really sort of illustrative. They're only about 30 seconds or so long, and you can get a lot of insight into what it means to track the position of a center of mass. But what I'd like to spend a little bit more time on to end this video is the classic rocket problem. I would like to sacrifice parts of my mass to propel myself. And it doesn't have to be for rockets. Let's say, for example, I was sitting in a boat and I happen to have a whole bunch of softballs with me. Now, initially, all of these softballs are in the boat with me, but I don't have a paddle. And I'd like to propel myself across the lake so I can get back to land. And so what I might do is start throwing a softball this way, and the rest of the boat and the rest of those softballs will go this way. Why is that? Because before I threw any softballs, I didn't have any momentum. So there was no momentum initially. Now I throw a softball. The softball has a momentum this way. For conservation of momentum to hold, the boat and the rest of those softballs and me have to go the other direction. That's the only way I can get zero momentum. So by me sacrificing little softballs every once in a while and winging them out of the back of the boat, I can actually propel myself across the lake using conservation of momentum. That's what's going on with the rocket problem in a much more extreme case. So let's say I have some rocket that consists of the mass of the rocket itself, plus a little bit of mass that I intend to sacrifice as fuel. And initially the rocket is moving at some velocity v, which means that it has a momentum of the mass of the rocket plus the mass of that little sacrificial bit of fuel times v. Now I'm going to take that little chunk of mass, delta m, and I'm going to throw it out the back of the rocket, giving it some momentum. It's going to be thrown out at a velocity v exhaust, and that little delta m v exhaust being chunked out of the back must, by conservation of momentum, speed up the rest of the rocket. So it might speed up from v to v plus delta v. So that means that the final momentum in this system is the momentum of that little chunk of mass, v minus v exhaust, the momentum of the remainder of the rocket, mv plus delta v, and this momentum, pf, has to be the same thing as pi because this is a closed system. So I set those two terms equal. I do a little, finding common terms, canceling them out and stuff like that. And what I find is this mass of the rocket times its change in velocity is the same thing as the mass of the fuel times the exhaust velocity. And if instead of distinguishing between mass of fuel and mass of rocket, we just said that the rocket was changing its mass, this differential change in mass becomes a minus d mass of the rocket at some instantaneous point in time. The minus sign just means that the rocket is getting smaller in mass as a function of time. So by me having my rocket getting smaller in mass, I can use that to propel myself to greater velocities. Interesting. Now I've got this dm over to here and an m. And I've got a dv that's shown here. What if I wanted to find how to calculate a change in velocity? I'm going to take this term here, this term here, this term here. I'm going to take this and I'm going to solve it for dv. And that's what we get in this line. Now if I would like to integrate both sides to find out what a final velocity with respect to initial velocity is, I do this by integrating dm over m. So integrating both sides, I get this natural log relationship. Rearranging terms just a little bit, it turns out that if you tell me what the initial mass and the final mass are, if you tell me what the exhaust velocity of the rocket is, I can tell you how the velocity is going to change. Now, that being said, this is a little bit weird. So whether it's a rocket, whether it's a person in a boat or something like that, as I start sacrificing little bits of my mass, if I throw faster, I can get to a final speed that's greater. But as I'm throwing out those little bits of mass, making my final mass of the boat or the rocket or whatever a little bit smaller, as I'm sacrificing this, I'm using it to increase my velocity. I'm using it to increase my velocity by using conservation of momentum. Interesting. Not only that, what if I wanted to find out this quantity of thrust? I mean, we've heard the term before, especially if you're in Florida and you've seen rocket launches, and maybe you've been to the Space Center and it talks about the thrust of a Saturn V rocket or something like that. What is that thrust thing, of the force that's going on? So I can take that exact same expression from above and actually take the time derivative of both sides. So I just divide both sides by dt. Well, m dv dt, that's just like a mass times an acceleration. because dv dt is like an acceleration. So this is going to work just like a force. Over here on the right-hand side, I've got this v exhaust, but dm dt is just a rate of me burning fuel in my rocket. So this is how the mass of my rocket is really changing as a function of time. Now, dm is technically a negative number. The mass of my rocket is getting smaller as a function of time. But if you just want to not think so much about the minus signs and plus signs, this really is a positive number. But if you don't want to worry about it too much and not lose too much thought, you can put an absolute value in here. But if you know the exhaust velocity of your system, and you see how your mass is changing as a function of time, that's what the thrust of the system is. Now from this, if I've got some scenario where the exhaust velocity of my fuel being burned is a constant, and I'm burning this fuel at a constant rate, this thrust is a constant. So this is a force that's being applied to the rocket that is constant. But the mass of the rocket is not constant, right? The mass of the rocket is getting smaller as a function of time, so that with this constant thrust, smaller mass as a function of time, the acceleration has to be getting greater as a function of time as the rocket burns its fuel. So that constant thrust leads to an ever-increasing acceleration as we go, because the rocket is getting lighter. This is not a constant acceleration scenario, and that's kind of what we see through this natural log behavior. Now, let's say we wanted to look at a specific problem, and I just kind of came up with this problem off the top of my brain. I know you can't see it yet, but I'll get there. So this is the problem I'd like to look at. Here I've got a rocket of mass 500 kilograms. It starts from rest and uniformly burns 70% of its initial mass at a rate of 70 kilograms per second. I would like to figure out a couple of things about the motion of this rocket. So how long was the burn? So it's burning at 70 kilograms per second, but it's burning 70% of its mass. So how long is the burn? I would like to find out what the thrust of this is, because I know the exhaust, I didn't write the exhaust velocity here. Let's make it 1,000 meters per second. So exhaust velocity. We can put that in. Okay. So we can find out what the thrust is. I want to find out what the final speed of this rocket is after it's burned 70% of its initial mass in fuel. And then I'd like to compare with maybe some numbers that we could see from kinematics. So looking at this, first of all, we want to find out what some burn rate is going to be. And for this, definitionally, what we might say is that time of the burn is going to be the change in mass divided by that burn rate. This is going to have units of kilograms divided by kilograms per second. This has units of time. Now the change in mass is going, if I'm burning 70% of my initial mass, I can call F 0.7, and my change in mass is F times the additional mass. I divide by the rate, 70 kilograms per second. Pulling up my calculator, let's do that here. So we've got 0.7 times 500 divide by 70. I've got 5 seconds. So we're burning for 5 seconds. Next, I'd like to find the thrust. And the thrust in magnitude and everything is the exhaust velocity. And then we have the rate of change in mass. Change in mass with respect to time. That's what this thing is. Change in mass with respect to time. That's it. We're burning 70 kilograms per second. That's how we're doing it. So the thrust of the system being constant, I can take the exhaust velocity, 1,000, times that rate, 70. Well, that math is pretty straightforward. The thrust is 70 kilonewtons, and it is constant. Maybe I want to find out what the final speed is. We found that V final minus V initial is V exhaust times the natural log of mass initial over mass final. And so we might want to keep a little closer tab, of what those masses are. My initial mass was m, but my final mass is only 30% of my initial mass. I've burned 70 away. So it's my initial mass minus the part that I burned. Or, because m cancels with m, 1 minus that fraction. So how does this look numerically? We go over here, let's just close this. Okay, so 1 minus 70%, 1 minus 0.7. I put that in the denominator, and I find the natural log of this, which is, where is natural log? Down here. 1.2 times the exhaust velocity, 1,000. So this is 1.20 kilometers per second. Sorry. That's pretty quick. Now, like I said, the last part of this problem says, well, why don't you compare this with what you might have found with kinematics? Because we know a force, and we know an initial mass, so we could find the acceleration, at least the initial acceleration, right? And then V final is going to be that acceleration times time. And so the acceleration being the thrust per mass times the time calculated above, we could look at that. So the thrust is 70 kilo, let's back up 1 here, times the time, which is 5 seconds, divided by the mass, 500. That's only 700 meters per second. That's different than what we found here. Why is it different? We don't have constant acceleration. Because the force, the thrust that's being applied is constant, to an ever diminishing mass, the acceleration is getting larger and larger and larger through this burn, which is why through this burn it gets to a much greater speed than if its mass wasn't changing at all. Because of that sacrificing of mass into this exhaust, leading to thrust, leading to change in velocity, I can do it much more rapidly because my mass is getting smaller. I'm accelerating more rapidly because of that. Now let's say I wanted to look at how this was changing as a function of time, because I could look at that too. Maybe I wanted to look at this change in velocity. Maybe let's say velocity as a function of time. If we're starting at rest, it's V exhaust, natural log of initial mass divided by final mass, right? That's what we were saying. And the exhaust velocity stays constant. This natural log is fine. My initial mass is m, but my final mass is whatever that initial mass is minus the burn rate times time. The burn rate being constant, kilograms per second, times a certain time in seconds, that tells me how the final mass of my system looks. So this tells me that my velocity as a function of time has this strange functional form. So looking at this, we've got a couple of things that we can see. And I'd like to take a quick jump over to Mathematica to look at this a little bit more substantially. So here we are in Mathematica. Okay. And here I have some exhaust velocity, I have some initial mass, I have some burn rate that I can determine myself, and I can figure out how much of my mass I want to burn. And if I wanted to, I could just keep burning. So I keep this constant burn rate and I burn and burn and burn, and I'm basically seeing the trajectory of my rocket, how my velocity is changing as a function of time as I burn my fuel. Now, our problem, we had a mass of 500 kilograms, we had an exhaust velocity of 1,000 meters per second, we had a burn rate of 70, so let's change this. And we wanted to burn 70% of our fuel. So what we see is our velocity as a function of time. It looks something like this. It says that, okay, this is 5, 10, 15, 20 seconds. Yeah, we burned for 5 seconds. That's what we said. And our final speed is going to be 1,000, 1,200, 14, 16, 18, 20. Yeah, so this is about 1,200 meters per second, 1.2 kilometers per second. This is exactly what we saw before. As I keep burning more and more fuel, sure, I'll get going faster and faster, but I fall along that path. Okay. Now, you might expect if I had a larger exhaust velocity, I'd probably get to greater speeds. I would get to greater speeds, sure. But because of my burn rate being constant, I do it in the same amount that the burn rate, getting to some certain fraction of the mass being done, I'm burning the mass at the same rate. But if I can exhaust it more quickly, I can get to higher speeds. That makes sense, even though the burn rate has not changed at all. Okay, that's interesting. Another thing we can see is what happens if my initial mass changes. It turns out that the initial mass in our calculation canceled out. Mass initial divided by mass final. If we knew we were just burning 70% of our mass, the value of that mass itself didn't matter. I didn't have to put 500 into that. So my change in velocity from 0 to whatever it is doesn't depend on the initial mass. Doesn't depend on the initial mass. But it turns out that if I have a larger mass, my constant thrust is going to lead to smaller accelerations. And so to get to that final velocity, it's going to take more time. As we see here, by changing that initial mass, it takes more time to get to that final speed. Okay, what if we were to change our burn rate? We started to not change our exhaust velocity, but burn fuel faster. Burn fuel less fast. Okay, that's totally fine. But at the end of the day, we're still burning the same amount of fuel. We're still burning the same amount of fuel, so that has nothing to do with this change in velocity that we're going to get. The burn rate was nowhere in that expression. It was as a function of time, so that tells us where we are on this blue curve. But as far as what the endpoints are, it doesn't have anything to do with it. Okay, that's kind of interesting. And so if we were to look at an extreme scenario, maybe we wanted to have a very low exhaust velocity. Maybe we wanted to have a very high mass. Maybe we wanted to have a very low burn rate. And we wanted to burn as much of our fuel as we could. Okay, so now we're looking at these times. So we're burning at a very low rate, but we're burning a lot of fuel. That's why we're spending a lot of time here burning everything. And maybe we have a lot of mass, which means we don't get a lot of change in velocity. Sure, if we were to change this, we could get, because our constant burn rate of kilograms per second, we're burning much different amounts of fuel, we get to different things. But we do see, if I could really crank up that exhaust velocity, I'm falling along this curve right here. As I burn at a particular rate, as I have a particular initial mass, and as I exhaust at a particular constant speed, as I burn my fuel, initially it might look linear, but eventually it starts to turn. Here what we see is acceleration is not constant. Velocity is a function of time, you'll notice here. Acceleration is not constant. Acceleration is getting bigger and bigger and bigger as a function of time because we have a constant thrust operating on an ever diminishing mass. And so now we get this curved behavior shown here. Now this is the case of the classic rocket problem. Now I wanted to illustrate this because essentially we're doing a lot of the things that we did from the past. Essentially this is a weird application of Newton's laws, right? Because momentum is built on Newton's laws. But I wanted to talk about these two final things just as we end up with this lecture. And I hope you found it interesting. As far as getting ready for the exam, I would know how to calculate thrusts. I would know how to calculate changes in velocity associated with these different masses, and obviously the algebraic equivalent of these things. I'm certainly not going to go into the weeds, but it is kind of an interesting problem of another case of looking at non-constant acceleration. And while that's a little bit weird, it is nice to know that I can actually use a concept as simple as conservation of momentum to propel myself if I ever needed to do so.